Okay, so we are now in the last video for 14.6, which is on triple integrals. And if you recall, at the onset of the very first video, I mentioned that triple integrals have dual purposes. They can calculate volumes and they can calculate mass. And I mentioned that the majority of the questions that I have ever done, in the majority of my training, anytime I ever needed to calculate a volume, I almost always used a double integral. But now you'll see the importance, specialness of a triple integral is when it's used to calculate the mass, centers of mass, etc., of, say, some solid. Now, just kind of going through the formulas that you're going to need. These should ring a bell, very similar. Just notice now that, so for example, the mass, when you set up your triple integral, you still have some density function inside your integrand. Only the density function is a function of 3 variables, right? So it's, x, y, z. Okay. The first moments, notice that each of these moments is about a plane, whereas the second moments, which we'll talk about in a second, is about a line. So the first moments about the YZ, XZ, or XY plane should also look similar. It's just going to be your density function, which will tell you the density at any point on the solid, multiplied by a distance. Okay? Finally, when all said and done, if you're looking for the center of mass, again, it's obviously the center mass is going to be some point on the solid, and you find each of those x bar, y bar, z bar by the quotient, right? And it's just going to be the quotient of the first moment divided by the mass. Now, for an application that is often where triple integrals are often used, I mean often used in engineering and physics, deals with moments of inertia, right? Or the second moments. And it goes a little something like this. If you have some mass, right? Some object of some mass, m, and you are trying to calculate how much time it'll take for that mass to reach a certain speed of rotation. Makes sense? So, right? So how much time before that mass reaches a given speed of rotation? Triple integrals and more importantly, moments of inertia are critical for answering questions like this. I'll say one more thing, just as I mentioned in the very first video of this section. When it comes time to integrate, right, we have dz, dy, dx. Now, the order of integration, right, the order dz, dy, dx, the order at which you integrate does not affect the solution, but it can obviously affect how hard the question is to integrate. Since I've spent a lot of time in 14.2 helping you set up bounds, helping you determine, what is the easiest order of integration when we had double integrals. I'm not going to spend a lot of time switching bounds. In fact, if you will listen to me for just a second, since we are doing this mostly cookie cutter textbook problems, I would like you to think, for the majority of the triple integrals that you're going to do, it's going to come in the form of dz, dy, dx, okay? Obviously, that's not going to be the case in the real world and most real life applications. But if you want me to just again, while we're here, just to make sure you understand. So since you have three choices, well, basically that 3 factorial, 3 times 2 times 1, that means you have 6 different ways of setting up the integration on a triple integral. So dz, dy dx, dz, dx dy, etc. You have 6 different ways that you could set up the order of integration. Do you understand? That's a lot of work to have to continue to go back and think about switching your bounds and moving things around when just to change up the order of integration. So my goal is to make sure you know how to use a triple integral. And I hope that my lectures in 14.2 showed you how to switch the order of integration and the bounds of integration as such. But I would like you to just be thinking dzy dx. Okay? So let's just go ahead and do one of these problems. And this will be the only problem that we'll do for, or this will be the last problem we'll do for this section. So we would like to find the center of mass of some unit cube. Now, unit cube is just, so we have a cube where length, width, height is all 1. They were nice enough to give us a picture. If not, we would have to obviously draw a picture. But we want to find the center of mass. So the goal is to find, x bar, y bar, z bar for this solid. But notice it says given that the density at the point xyz, now that's some arbitrary point, right? In other words, the density at any point is what that's saying, is proportional to the square of its distance from the origin. We need to make sure we can translate that, because they are not giving us the density function. We are going to have to use that information to form the density function. So right off the bat, as soon as you read proportional, you want to think some constant of proportionality k times something, right? We need to figure out what that something is. Now, proportional to, well, it says the square of its distance from the origin. So from the origin, well, that's 0, 0, 0. So to this arbitrary point on the solid, x, y, z. But distance, that's quite easy, right? I mean, distance is just equal to the square root of, well, that's going to be x minus 0 squared plus y minus 0 squared plus z minus 0 squared. Now, but we don't want the proportional to the, it doesn't say proportional to the distance. It says proportional to the square of its distance. So d squared, all right, so we'd have to square both sides. And of course, x minus 0 is just x, so it's going to be equal to x squared plus y squared plus z squared. That is what the text that I highlighted above and translates to be x squared plus y squared plus z squared. So that plus that constant k forms our density function. All right, so we now have our density function. So at this stage, we are going to start with our mass. And we know that we're going to place that density function inside the integrand of our triple integral. Now, I just got done lecturing you on how you should want to think dz, dy, dx for these integrals, triple integrals that I'm going to throw at you for this class. But not only does the order in which you integrate not affect the solution, but in this particular problem, just due to the symmetry of this cube, it doesn't even affect how hard the integration is. So no matter how you set up the integral, it's going to be the exact same calculations. And that's simply because in each direction we're bounded from 0 to 1, right? 0 to 1, 0 to 1, 0 to 1. So all of these integrals are from 0 to 1. So it was unfortunate that they didn't give us a density function. We had to build that. But it is pretty nice that at least all of our bounds are constants. So at this stage, we just get busy. We just get busy with the setup for integration. So we'll just go right through, start integrating with respect to z. So 0 to 1, 0 to 1. You can bring that k out front since it's a constant. And let's go. So we're integrating with respect to z, treating x and y as if they were constants. So that's x squared z plus y squared z. And that's going to be plus z to the power of 3 over 3. So we still got 2 more rounds of integration to go, but we got to back substitute first. So we're going to be plugging that, we're going to be plugging, you would plug the 1 and the 0, right? But obviously, you can see that if you plug 0 in for z, that's just going to zero everything out. So really, it's just a matter of plugging 1 and just making sure we plug it in this case, for z. So what does that give us? Well, that just gives us x squared plus y squared plus 1/3. So let's get started. One more round of integration. I will say something really quick. I don't, when you're watching a lecture, when you're, watching a lecture live, watching a lecture on a video, it's pretty easy to think to yourself, well, I wouldn't make the mistake that the professor is warning me about. But when you are under a lot of stress for taking tests, a lot of times we do make silly mistakes. And I've seen students take this constant of 1/3 and bring it out. And that is a mistake. Because that term, if you brought that 1/3 out here, you are saying that it's distributed to everything, which it is not, right? It is, in other words, we can bring multiples, factors, constants out front, right? But not terms. We don't move terms around like that. So we'll leave that 1/3 the way all that, just to say leave the third alone, and let's keep integrating. So now we're going to go ahead and integrate with respect to y. So that's x squared y plus y to the power of 3 over 3 plus 1/3 y. All right, one more round of subbing 1 in for the y variables. So let me go ahead and finish this up. So this is going to, if you plug 1 in for y, x squared times 1 is just x squared. Let me go ahead and save myself one step. So plugging 1 in for y here and here. So that just is 1/3 plus 1/3, right? So 1/3 plus 1/3 is 2/3. All right, and let's finish it. So we got now last round of integrating with respect to x. So that's x cubed over 3 plus 2/3 x. One more round of subbing. And what you're going to see is if you plug 1 in here for this x, you'll get 2/3. If you plug 1 in here, you'll get 1/3. So you have 1/3 plus 2/3. In other words, you have 3/3 or 1. So that is your mass. All right. So I'm going to save us a little bit of time. Remember, the goal is the center of mass, x bar, y bar, z bar. Because of the symmetry. Well, let me go ahead and let me just write before, and then I'll talk about what I'm trying to say. So you would normally calculate the moment about the YZ plane, the moment about the XZ plane, and the moment about the XY plane. You would have to calculate all of them. But due to the symmetry of this cube, you would find that they are indeed all going to be equal to each other. So whether you had noticed it at the beginning, noticed due to the symmetry, or you noticed it just by, after you jumped in, you really are only going to have to set up one of those integrals because they are all going to be equal. I'm just going to go ahead and just set up one of them for you, and then I'm going to jump right to the solution. So if you want to find, let's say, the moment about the YZ plane, so your triple integral, still going 0 to 1, and the formula is x multiplied by the density function, which in this case, the density function is x squared plus y squared plus z squared. So not bad. If you thought, as long as you found the integration that I did up here easy, then all you would do is distribute this x, and the integration would not get any harder at all, okay? So let's assume that you were to go through all of that integrating. You would find that the first moment about the YZ plane is equal to 7k over 12. And as I had mentioned, the good news is I'm gonna save us some time with this easy problem, in that all of our first moments are going to be 7k over 12. Now, the only thing left to do is to, again, find x bar, y bar, and z bar. So I'll just do x bar for you. So that would be the first moment about the YZ plane divided by the mass, which in this case would be 7k over 12, divided by mass, which we saw was just k. Well, what did we get? Well, we just get 7/12. And that 7/12 is going to be the same for all of your first moments. I'm sorry, for all of your x bar, y bar, z bar. So y bar is also going to equal to z bar. It's equal to x bar. Okay. So in that case, let's just again, you've done all the heavy lifting. You have the problem answered. But if you just leave it like this, it's just really sloppy, right? I mean, I wanted the center of mass. Your client wanted the center of mass. So give them the center of mass. Give it as a point. And then we're done. See you guys in the next video.